Hello, and welcome again to your OCHEM 2 course. Today we're going to be looking at the synthesis of Stilbene. The reading material should be available on your textbook on section 28, pages 366 to 370. These are the physical and chemical properties of Stilbene. We're going to be working with two different isomers, both the trans and the cis. Both have similar molecular formulas, similar molecular weights. The appearance is different considering the steric hindrance of both molecules. The melting points are completely different. And while both of them are not miscible in water, only the cis form presents a boiling point. Here we show the reaction scheme of the synthesis of the stilbene that we're going to be making from benzaldehyde. So our benzaldehyde molecule is going to react with benzyl triphenylphosphonium chloride in the presence of NaOH in DCM, forming a mixture of the E and Z stilbene, which is the same as cis and trans. Byproducts of the above reaction are going to be the triphenylphosphine oxide, sodium chloride, and water. How do you make the benzyl triphenylphosphonium chloride? This is a very important reagent for the synthesis that you're going to make. And here we show a little bit of the synthesis about it. So we're going to take commercially available triphenylphosphine and react it with benzyl chloride. So it is important to note that any halogen is fine for this reaction. So it could be benzyl chloride, could be benzyl bromide, could be benzyl iodide. Either one of these is a good leaving group that it's going to undergo a nucleophilic substitution reaction upon the nucleophilic attack of the phosphine. This way we will form this salt, the benzyl triphenylphosphonium chloride, but this compound is going to be provided to you. Next, we're going to make the synthesis of the Wittig reagent. This is called the Wittig reaction, which is a very important reaction that's seen in your OCHEM courses. Discovered by George Wittig, and this gave him the Nobel Prize in 1979. So the benzyl triphenylphosphonium chloride reacts with the basic NaOH. Basically, these hydroxyl groups take one of the protons to form water, to form sodium chloride, and to form the Wittig reagent. The Wittig reagent, which is basically a double bond between the phosphorus and the carbon, then undergoes a resonance structure where it turns into the ylide form. It is important to know that formation of the ylide is very noticeable as the reaction will turn yellow. So an ylide is a molecule that has both a negative and a positive charge next to each other. So the carbon ion is going to attack the benzaldehyde, and it's going to incorporate the benzaldehyde skeleton into the whole system. Upon doing this, the negative charge that was trespassed to the oxygen will come back, and it's going to attack the phosphorus, which has a positive charge, making the oxaphosphatane, which is a four-member ring. The oxaphosphatane is a rather unstable molecule that will undergo bond breaking, giving us the triphenylphosphine oxide and a mixture of the cis and trans stilbene. This is the last step of the synthesis, and you're going to be able to notice the completion of this reaction upon the elimination of the color. The reaction should turn transparent again, and that's when you know when to stop. So we will perform these steps, number 1 and 3, in the separatory funnel. This is the laboratory procedure, so let's go through it really quickly. In your step 1, you're going to take 125 ml separatory funnel and a right-sized glass stopper. This is important because the reaction is exothermic and it's going to release a lot of pressure. So using a funnel, we need to add 3.9 grams of benzyl triphenylphosphonium chloride. We need to wash any remaining powder with 15 ml of dichloromethane, or DCM. Add from 1.1 to 1.2 ml of benzaldehyde. Then add 40 ml of 50% aqueous NaOH solution. Shake the separatory funnel for 35 to 40 minutes and occasionally vent the pressure by taking off the stopper. It is important that since in this lab you're working with a partner, you can take turns since it's a very long reaction. You're going to add 20 ml of dichloromethane and shake gently. Settle down the separatory funnel to separate the layers, then drain the lower aqueous NaOH layer in the beaker. So even though DCM is denser than water, an aqueous solution of NaOH happens to be denser than DCM. So in this case, the lower layer is going to be the aqueous. This is really important to know because there is a lot of confusion considering that nothing has color in this reaction. We're going to add 10 mL of tap water into the separatory funnel and shake gently. This time, the water is less dense than the DCM since it doesn't have any salts dissolved in it or any NaOH. So we collect the lower DCM layer in an Erlenmeyer flask. We're going to add magnesium sulfate into the Erlenmeyer flask to dry the solution, and then do gravity filtration to remove the magnesium sulfate. Collect the filtrate in a beaker. Label and store your solution in the proper cabinet for next week lab. Remember, every product in this synthetic strategy is going to be stored unless told otherwise. Here we will just recall very rapidly how to do the gravity filtration setup using the filter paper and what we're expecting to do. There are a few things we need to pay attention to. Shaking the separatory funnel with volatile solvents like DCM will create a lot of pressure inside of your separatory funnel. So occasionally, every few minutes, release the pressure by removing the glass topper to avoid any spill. 50% NaH solution is extremely corrosive, so you must wear the safety goggles and gloves at all times while working in the lab. Serve yourself of as many safety gloves you need in order to make this procedure. If 50% NaOH solution is spilled on your skin, immediately wash thoroughly under running tap water. Dichloromethane is very volatile and toxic. Always keep your reaction flask inside your hood and away from your face. The waste disposal and cleaning. So the solid waste, which is going to be the magnesium sulfate. We're going to have aqueous phase waste, which is the aqueous 50% NaOH solution from the separatory funnel, and the tap water as well. We're going to have halogenated waste, which is any additional dirty dichloromethane. So for cleaning, clean the glassware with soap, water, and if needed, acetone. You should request this to your TA. Clean your hood with soap, water, and paper towels. Also, make sure to clean the balance area to avoid any loss of points. And for the TA only, I need to ask all of you to clean any additional dirty glassware that we see in the lab. Remember, we need to work as a team to keep our environment clean.